Okay. So, in the last class, we had been discussing about transmission lines. So, basically, there, what we wanted to see is that in general, for our like circuits where the frequencies are not that high, or the cases where we can consider them as lumped circuit, we don't take into account the effect of the connecting wires, right? But then there can be a regime where the dimensions of your connecting leads are comparable to the wavelength of the signal, and in that case, one has to consider the effects that come in because of the wire. Okay, and there it was seen that one can represent the wires as some distributed parameters, which includes resistance, conductance, inductance, and capacitance. Okay, and in terms of that, we can, uh, in a way, you can say, model the effects of the wires or the connecting leads. Okay, so that was about the transmission lines. So, what we'll mostly talk about today is a graphical method of solving this problems regarding transmission lines and how one can find the impedance or reflection coefficients or standing wave ratio and things like that through a graphical method. Okay, and that is what is called the Smith chart. So we'll first discuss some basic concepts and we'll try to solve some problems, and if you have some particular doubts, we'll try to address that. So what basically is the Smith chart is it's a graphical plot. Okay, and it's a graphical plot of normalized reactance and and resistances. Okay, in the reflection coefficient plane. So there are two main important things here. One is the normalized resistance or reactance, and then the reflection coefficient plane. So what we mean by that? So first, normalized reactance or resistance means that we have to normalize them with respect to the characteristic impedance of your transmission line. Okay, so suppose your load impedance is ZL, and then you have your characteristic impedance of your transmission line is Z0. So you normalize it with respect to Z0. So that's your normalized resistance and reactance. Okay. Now we want to represent this on the reflection coefficient plane. Now, what do we mean by the reflection coefficient plane? So if you remember, this is what is the reflection coefficient, right? So it's the ratio of the, you can say, the amplitudes of the reflected wave to the incident wave, right? And this is how they are related to the load impedance and the characteristic impedance of the transmission line. So here now your ZL, the load, can be complex. So that tells us that your reflection coefficient can also be complex. And if it is a complex number, you can represent it in a complex plane, right? And that is called the reflection coefficient plane. So this is basically a way of representing your normalized resistance and reactance on the reflection coefficient plane. Okay. So any point on the reflection coefficient plane will correspond to some value of the reflection coefficient, right? And that is related to some load, some load, and then it will have both. So it's in the complex plane. So that means in general, it can have real parts and imaginary parts. So it can have resistance and reactance involved in it, right? Now, one can also use it as an admittance curve where things get 180-degree phase changed. Okay, so we'll discuss about that. But what we do with this Smith chart, so what is the aim of using it is that you can find the reactance, reflection coefficients, you can design matching networks, or you can also determine the standing wave ratios of your given circuit, okay, using the Smith chart. And this is a very easy or graphical method that gives you a qualitative understanding of your circuits. And if you have to engineer, like in microwave or RF engineering, this Smith chart is very widely used. Okay. And it's named after the inventor P.H. Smith. Okay. So now this is how a typical Smith chart looks like. Okay. And if you are in the impedance, so if you consider this as an impedance chart, there what will happen is this first, like the upper half is the inductance plane, and the lower half is the capacitance plane. It's basically because of omega L and 1 by like j into 1 by omega c. So this 1 by factor, right? So because of that, the upper half is the inductance plane and the lower half is the capacitance plane. Okay. And anywhere in this line, it's a purely resistive impedance if you move along this line. So we'll see how and why. Okay. And all of this, as you can notice, there are some circles here, right? So all of these circles are circles of constant resistances. Okay. And then you can see another kind of, arcs here, right? Like this lines, if you consider. So they are a part of some bigger or some other circle. So they correspond to the X circles, which we'll also talk about. And here, so when we are talking about impedances, the resistance increase inwards. Okay. So this is the point of your short circuit. So the big circle that you can see, if you follow this line, that big circle will correspond to R equal to 0, while as you come inwards, somewhere here, it would correspond to an open circuit, right, where R gradually tends to infinity. So why so? It will come mathematically as well, but this is how a typical Smith chart looks like. Okay. So now, what is this Smith chart? Basically, here each point corresponds to some load, right? Some ZL value. So now, in general, your ZL can have a real part and can also have an imaginary part, right? So you can write it as RL plus JXL, and then you have to normalize it by R naught, right? So if you do that, now this part of this is small r, and the imaginary part is given as small x, right? So basically your normalized impedance can be written as small r plus j into small x. Okay. So now if you know, this is how the reflection coefficient looks like. So we know the relation between the loads and the reflection coefficient, right? And the reflection coefficient can be complex. So you can write it as the real part and the imaginary part. Okay. And then if you divide like ZL by R naught minus 1 by ZL by R naught plus 1. So if you do that, then you get this form, right? So in a way, now what you can do is you can write ZL in terms of the reflection coefficient. Okay. And it's a complex quantity. And then if you try to write it, you expand the reflection coefficient as omega r gamma r plus j gamma I. If you do that, then you get something like this, right? So now it's a complex quantity, and you can do all the normalization and simplification to find out what is the real part and what is the imaginary part, right? So if you do that, what you get is something like this. So this is your real part and this is your imaginary part. Okay. So now we'll see that, starting from these expressions, we can how we can visualize. So I told you that these are, the R circles, but how do we get to that? We start with these equations. Okay. And now suppose you start with the first equation. So here what you see is R for any value of resistance. Okay. Of the real part of your normalized impedance. So for that, any value of R, you have this kind of dependence on the real and imaginary part of your reflection coefficients, right? So if you solve it, like just try to rearrange and solve, you would get an equation like this. And this is actually the equation of a circle. Okay. So that means in the reflection coefficient plane, what do you mean by reflection coefficient plane? Each point here corresponds to some real part of the reflection coefficient and the imaginary part of the reflection coefficient. And that actually corresponds to some load impedance, right? So now, if you write it in terms of, so this is your the real part. So this is like this along this line, and this is along the perpendicular line. So that's the complex plane. So in terms of the reflection coefficient, in the reflection coefficient plane, you get a equation of a circle. Okay. And then this is this gives you the coordinates. So R by 1 plus R comma 0, that gives you the coordinates of your circles, right? And this gives you the radius of your circle. Okay. So what this tells you, that the centers of all circles lie on the gamma r axis. So what do you mean by the gamma r axis is this line. So as you can see, for all of these cases, it is along this line, right? And then the r equal to 0 case. So if you put r equal to 0, what you get is an unity radius circle, okay, circle of radius 1, and it's centered at the origin and it's the largest. So it's this big circle that you can see, right? And now gradually as your r increases, you gradually move inwards, okay? So this is your short circuit, this is your open circuit, okay? Now, if you go, all this happens when you are in the impedance, when you consider the Smith chart as an impedance representation, okay? But if you go to admittance, admittance is 1 by impedance, right? So in that case, it gets reversed, 180-degree reversed. So in that case, this will be your short circuit and this will be your open circuit, right? Okay. So now all our circles pass through this point. So 1 comma 0. So what is 1 comma 0? This is your 1, okay, and then 0. So all the circles pass through this point, okay? So these are the characteristics of constant R circles. So along this line, along each of this circumference of the circles, your resistance remains constant, right? And this is the purely, so this line is the purely resistive line. Okay. Now, if you do the same thing for the X expression now, you get something like this, right? And from there, you can plot another circles which would look like this. So this circles are called the constant X circles, okay? And again, here you can see that this part would be the inductance part, inductive reactance, and this would be your capacitive reactance, right? And the X equal to 0 circles, if you put X equal to 0, it becomes what? It becomes this line, right? It is this line, because along this line, it's only purely resistive, okay? And then X becomes progressively smaller as you move from 0 to infinity. So it's like it again progressively becomes smaller, okay? And all X circles pass through this point. So as you can just see from the figure or the Smith chart, okay? So these are the characteristics of your constant X circles. So any point in this upper plane, if you move along these lines, it would be some inductive reactance, and similarly here it would be some capacitive reactance. Okay. So now that means that you can, so each of these points would represent some complex quantities, right? And so if this is how your Smith chart looks like, if you look at a any given Smith chart, you would see that there are numbers there, okay? And so suppose if you have to plot some complex quantity 1 plus j1, right? So how do you plot it? So it's like like this. So your j value should be, so let me see a, right? So now here what it means is the real part is 1, so it should be along this line, right? So that your resistance part is 1, okay? So it should be along this circle. Now along the circle where, so it's said that the imaginary part is again 1, so then you can go along this line and the intersection of this, so this point, it gives you this particular complex quantity which can represent some impedance, right? Some normalized load impedance. So similarly, like these are different examples which shows how, so you can do this exercise, and it's taken from the same lecture that that is there in NPTEL. So basically you can choose any of the quantities. So somewhere in the middle, then you have to guess like where, it's there. So basically this is an exercise which tells you that if you have, or if you know the normalized impedance, how do you plot it in your Smith chart? Okay. Now, what does these things mean? We'll gradually come to this in the coming slide. Okay. So in order to understand the Smith chart, these are certain things that you should remember. So we know what is a reflection coefficient, right? So that means there'll be, that tells you that if it is not matched properly, there'll be some signal which will be reflected back, and it's the ratio of the reflected to the incident or the forward moving signal. Okay. So now suppose if you have some signal where you have some load resistance or some load impedance, and this is the characteristic impedance of your given transmission line. And this here is your this shows your source or your generator. Okay, so basically there are 2 points where the impedance needs to be matched in order to have a complete transmission, like in order to have zero reflections. So one matching should happen at this end where Z naught should match with ZL, and again your Z in the other end, your ZG should match with Z naught, right? So now suppose in the we take into consideration the lossless case where your Z naught is real and your uh, gamma can be written as J into beta. So alpha is 0. There is no attenuation. So in that case, now this is some convention which tells us that suppose at this end, so this is your source end where you term it as Z equal to 0 and you have the load at some Z equal to L. Okay. And you can define a quantity D which moves in this direction. So D and L and Z are related by this relation. So at the source, your D is equal to L, and at the load, your D is equal to 0. So you gradually move from here to here, 0 to L. That's how your D changes. Okay. So now we know that at any instant, any Z, this is how your signal will look like. Okay. And you know that the ratio of V0 minus to V0 plus is your reflection coefficient. And in general, this is an imaginary quantity, complex quantity, and you can write it as some modulus into e to the power j phi L, where this is your argument. Okay. So in the Smith chart representation, you can represent it by some vector like this, right? So it has a magnitude of gamma L, and then the argument is phi L, right? And now what you do is at some point Z, so anywhere along this line, somewhere at some Z, if you want to write how the reflection coefficient looks like. So in that case, what will you have to do? You have to, so that then you have to divide by this entire signal, right? So V0 plus e to the power minus gamma Z by, V0 minus e to the power gamma Z by V0 plus e to the power minus gamma Z, right? So if you do that, this is what you get. So this is the reflection coefficient at any particular Z, right? And this is your magnitude of this thing. So this is what you get from here, right? And now what you do is you just break it up in terms of this expression. Okay, so Z is equal to L minus D. So if you substitute it here, and you know that in general, what is your gamma? Your gamma is alpha plus J beta, right? Later we'll put gamma as only J beta considering the lossless case. But in general, this is how it will look like. Okay, so if you take together all the terms which are independent of D, you would be getting something like this, right? So this is some term which does not depend on D, but this depends on D. So D is the variable that tells you where you are, okay, in the transmission line. From if you start from the load towards the source, where you are. And what this is telling you is that now, depending on your position in this line, so depending on the value of D, your reflection coefficient at that instance changes, right? It gets some added phase, right? So suppose now if you put alpha equal to 0, you would get something like this, right? Where here you have this small l and this, so gamma small l, this includes all these terms. And again, if you put alpha equal to 0, you would get something like this. E to the power 2 j beta L is not very important because it doesn't add anything to the amplitude, right? So it's just a phase. So if you average, like if you find the modulus, it would turn out to be the same. So now what you can say that at any particular D value, your reflection coefficient will have a form like this. So it has this kind of dependence. Okay. And then if you say that this is your value from here, so this is your the reflection coefficient at this instance, then this is how it will look like at some particular D. Okay, remember that this magnitude is the same, so the magnitude does not change. Okay, only the phase gets changed by 2 beta D, where D is your distance from the, considering that at load it's 0, so how much distance you have moved towards your source. Now if you consider that beta is given as 2 pi by lambda. So now this is d equal to lambda by 2. Okay, if lambda is your signal wavelength, then when your d becomes lambda by 2, you acquire a phase of 2 pi, which is same as the initial signal. So that means that if one moves by lambda by 2, we get the same point on the reflection coefficient plane, right? So what we are basically doing is we are trying to represent the reflection coefficient in a plane, right? So that means if you come back by lambda by 2, you would come back to the same point on the reflection coefficient plane. Okay. Now, there are two things. So this distance, okay, this distance can be calibrated on the Smith chart in terms of the wavelength towards generator or the wavelength towards load, according to those scales, right? So I'll show you in the coming slides when you look at the Smith chart that how by looking at that scale you can tell how far you have moved from the load towards the generator, and depending on that you can acquire you can think of what the phase will be. Okay. Now all this is like so this kind of circles that you saw, that is true when in the lossless case, but if it is a lossy system, there it would become a spiral, because then you would have a so here this term would still remain, so then your amplitude will be exponentially decreasing, right? So there it will then it will be a spiral. Now one thing to remember is that so when you represent so when I solve some questions, I think it will be clearer. But so if you have some circle, okay, now how do you say what is the maximum value of the resistance on the transmission line? So that is given as Z naught into the standing wave ratio. Okay, so in a way now I'll show you how that if you have some circle, okay, some impedance, some normalized impedance, you draw a circle out of that. So that means the minimum and the maximum value of resistance which you will get from the gamma R axis will will give you the value of the standing wave ratio. Okay. And similarly, 1 by the standing wave ratio will give you the minimum value. So we'll see how to see it graphically in the Smith chart. Okay. Before that, let us, through these questions, just get ourselves cleared of some of the basic concepts. Okay. So now, which of the following are correct? So it says that the Smith chart is a graphical indication of impedance. That's okay. And of the transmission line and of corresponding reflection coefficient as one moves along the line. So this is true. This has no doubt. This is no doubt. Now it says that lambda distance on the line corresponds to a 720 movement on the Smith chart. So is this correct? Right? So what do you can you tell me is if this is correct or not based on whatever we had discussed? Yes. So it's because lambda by 2 corresponds to a 2 pi phase, right? So that means lambda corresponds to 720-degree phase, and you come back to the same point in the Smith chart. Now, the third point says that the admittance chart can be obtained by shifting each and every point on the impedance chart by 90 degrees. So what is your take on this? Do you think this is correct or this is wrong? So remember that admittance is given as 1 by reactance, right? Any idea? So that means, when we say, suppose, think along this line that you can do it. Okay, did I get a R equal to 0 is the largest constant R circle, right? Yes, yes. So if you look here, you would see that, see, this is the point where your R is equal to 0, right? So this is your constant R equal to 0 circle. Okay. Similarly, this is your R equal to 1 circle, which you call it as the unit circle. Okay. So, okay. So now when we talk about admittance, admittance is 1 by reactance, right? So this 1 by means you are adding a phase of 180 degree to it, or you can think it along this line that what we say is this is purely inductive, this is purely react. So anywhere along this line, so suppose along this line, this point, suppose. So if you look at B, what do you see? You see something like this, right? 1 minus J1, right? And somewhere here, what you see is, so if you look at 1 plus J1, so what kind of a phase difference are you getting out of this? So what is happening here? See, is a change from plus to minus in your plane, right? And basically that tells you that this is an inductive load, while this is a capacitive load. Now, if you think how do you write inductive load? You write it as omega L, right? And j omega L, and this you write it as 1 by j omega C, right? So that means there is a 180-degree phase difference there, right? So that means when you go from, so that means 1 by something, whenever you're doing any impedance and you do 1 by of that, so the reciprocal, that is actually a phase difference of 180 degree, not 90 degree, okay? So this is wrong. Now, what other thing that we see is, yes, so this is wrong. Now counterclockwise movement on the chart corresponds to moving towards generator, right? So this is something that we need to discuss. So see here, how do I tell you here? Okay, so here what do you see? As you move from the load towards the generator or the source, you acquire this phase, right? And this phase is given as e to the power minus 2j beta d. So this minus sign is there, right? So if the initial phase was some phi L, right? How will the phase change? So this is some phi L. Now that means it's decreasing, right? The phase term will decrease by this amount. So that means there's a movement in the clockwise direction, right? So that means when you move from the load towards the generator, there is a clockwise movement that will happen on the Smith chart, right? So counterclockwise movement on the chart corresponds to moving towards the generator. So this is wrong, right? Clockwise movement on the chart corresponds to moving towards the generator because the phase decreases by 2 beta d as you move from the load towards the generator. So in this case, the answer would be 1 and 2 only. So only these two are the correct options. Okay. Clear? Okay. So now this is another question which says that when the load impedance is equal to the characteristic impedance of the transmission lines, okay? So that means ZL is equal to the characteristic impedance, that is Z naught of your transmission line, then the reflection coefficient and standing wave ratio R. So this is a very, you can say, standard or fundamental question based on our understanding. So what do you think the answer should be? So ZL is equal to Z naught, right? So what should be the reflection coefficient and what should be the standing wave ratio? 4. Okay. So that means the reflection coefficient should be 0 because there will be no reflection because the impedance have already got matched, right? And if the reflection coefficient is 0, that corresponds to standing wave ratio of 1, right? So you do it by something like this. So this is how you define your voltage standing wave ratio. Okay, so V max by V min. So, and that is related to the reflection coefficient by this relation. And this is how the load impedance and the characteristic impedance decide the reflection coefficient. So if you put those values, you will see that your reflection coefficient is 0. And then that also tells you that your standing wave ratio is 1. Right? So this is your correct answer. Right? Now, this is a question which says that now you say the impedance is given as, so its impedance is purely imaginary. So there is no resistive impedance here. Okay. Only imaginary part is there. Now, and that is given as x. So z equal to jx. Okay, for all values of x, it can take all values from minus infinity to infinity. So how do you represent it on the Smith chart? So Based on what we discussed, can you think of what the answer should be? So in general, Z, for a normal Z, Z would be given as R plus JX, right? In this case, you only have the imaginary part. So your R is equal to 0, right? Yes. So if R is equal to 0, basically what this question is telling you is that you want to plot R equal to 0 circle on the Smith chart, right? So now if you go back, you would see that, right? So we just discussed that the R equal to 0 would be something like this, right? And you can also get the expression from here. So what you do, you put R equal to 0. So if you put R equal to 0, this term goes away. So that means the center is at 0, 0, right? So that is the center of your circle, and the radius is equal to 1. So this is your unit, this length is 1, okay, and the center is at 0, and you draw a circle out of that, and that is equal to your R equal to 0 circle, right? So basically that's what the question is asking you to plot, okay? So it would be something like this, right? This is the big circle that we see in the Smith chart, okay? So for any value of Z, if you are asked to find how, for how do you represent that impedance, or how do you represent that point, you have to think of this coordinates, okay, how the circles vary, and accordingly first put a point. Now if you are asked to find a circle corresponding to that, right, that would give you, that we call it as the SWR circle, or you can say the gamma R circle, and we'll see why. So that will depend on there. Suppose if it was some random point, then it would be some random circle, right? But basically it comes from first plotting the value. So here that means what it is telling you, is that your R is 0, right? So you're somewhere in this line. Now, when you put R equal to 0, you can always put it in these expressions to find the equations of your circles, and that will give you the plot in the Smith chart. Okay, so now this is another question which says that the impedance characteristics on a Smith chart repeat after a distance of. So this is already something we have discussed, right? And this should be lambda by 2, because every lambda by 2 distance on the Smith chart corresponds to a 2 pi phase. So you come back to the same point, right? So now, based on whatever we have discussed, we'll try to solve some Smith chart problems. And these are very standard questions which tells you the applications of Smith chart, right? So by looking at the chart and graphically, you can actually find different quantities. So you'll see what, okay? So suppose this is your given circuit, some circuit. You know the characteristic impedance of your circuit, and this is how your load is given. Okay, this is your load impedance. And you say that the length of your transmission line is given as 0.1 lambda. Lambda is your wavelength of your signal, right? So now it's said that first you have to locate ZL. So that this is the first thing you should learn, is to locate the normalized impedance on the Smith chart, right? So what is normalized impedance? So normalize ZL by Z0, and that this is what you get. Okay, so how do you point it on the Smith chart? Let us see that. So you look at the case where R will be equal to 0.1, and the imaginary part. So R equal to 0.1 comes from here. So you see the R point along this line, okay, and then take up the corresponding circle. So this is your R equal to 0.1, and then you see where along this lines, all these lines that you are seeing, which corresponds to 0.5, and that intersection will give you the ZL point, right? So this is your normalized impedance, okay? So this part is done. Now it says that from here, can you find the impedance at L equal to 0.1 lambda? So if you know the normalized impedance here, what would be the impedance at this end? This is what you want to find. Okay, so how do you do that? So what we do is we extend this along this line. Okay, and along this line, what we get is, this point that you are seeing here is your wavelength towards generator scale. So this tells you your point or the distance where you are from the generator, right? And we know that this is your location of your load, right? So you want to find that angle, right? So this gives you the angle, so that this angle, some not angle, sorry, some distance that corresponds to this position, right? So you mark that. Now what it says that you have to travel 0.1 lambda distance. Now you're moving towards the generator, right? So you have to move clockwise, right? So you cover a distance of 0.1 lambda. So you go to somewhere here, right? You note down the value of this distance. So this is your new position, right? In the Smith chart. And now if you extend back to your same circle, or your circle which corresponds to this radius, right? This was the radius of your load impedance, normalized load impedance, right? So if you do that, the point where it intersects, so if you draw this line and you have this circle, the point where it intersects is the impedance, or the normalized impedance to be particular, at this distance. If it was some other distance, you would have moved by some other distance, right? And then you would have drawn a line, and then this will be a part of a circle, right? This is a circle. So that circle, wherever it intersects with this line, which you would draw from this starting point, would give you the impedance at that particular length, right? So now that gives you the value of normalized impedance. If you are asked to find impedance, what you have to do? You have to multiply by the characteristic impedance of your circuit, right? So that's what is being done here. So that gives you the value of impedance at this length, right? So in normal questions, suppose if you have to match the impedance, first you have to know, right? So what is the impedance that you get at this end? Only then you can. So basically you need to, suppose you have some generator and you know the impedance at the source end. You want to see whether it's matching or not. So in order to do that, you have to first find what is the impedance here, right? And this is how you find the impedance from the Smith chart graphically. Okay, now it says that what is the standing wave ratio on the line, right? So here what we do is, see, you draw a circle of this radius. So if you draw a circle, what is this circle corresponding to, right? So this circle corresponds to all the impedances which has this particular magnitude, right? This will give you some magnitude, and depending on that, so all the impedances will be covered along this line, right? So now if you draw this circle, what happens when it intersects this horizontal line? So that means at this point, it's a purely resistive load, right? And we know that the resistance increases from outwards to inwards. So this point gives you the maximum resistance on the line, right? And similarly, if you would have drawn a complete circle, you would have got some point here. Okay, so if you extend the circle, and that would correspond to the minimum resistance on the line, right? So we know that the maximum resistance on the line is actually the standing wave ratio, right? So that gives you the value of VSWR, right? So if you do that, the point where it intersects, that point gives you the maximum resistance that is there on your line. Okay, so this is how you do this. Now, here it says what is the reflection coefficient, basically the magnitude of the reflection coefficient, right? So that means what you have to basically find is the length of this quantity. So here in this case, you have scales defined on the Smith chart. So what you can do is you can measure this distance, by some scale or something, and accordingly, or a protector, or and then you just match it with the length that it covers on the scale, right? And that gives you the magnitude of your reflection coefficient. But the reflection coefficient will also have an argument, right? It's a complex quantity. So how do you find that? So what you do is you take the angle that it makes with this line, right? So if you take that angle will come from this scale that you see right here. It suppose, as you can see, it's 120, it's 130. Where it intersects, it makes an angle of 126.5. So this is your argument, and this is your magnitude. So now you know the reflection coefficient. So that's how you can find reflection coefficients for your given circuits. Okay. Now, what is the reflection coefficient? So this is the reflection coefficient at this terminal, right? This was the starting point at the load. Now, what is the reflection coefficient here, right? So at 0.1 lambda distance from the load. So what you have to do the similar thing. Now we know that this was the point of your impedance, like normalized impedance at 0.1 lambda distance from the load, right? So we don't need to find the magnitude again because we know that the magnitude remains same. So this would remain same. What has changed is the angle, okay? And it has moved by this angle. So what you can do is you can find one thing you can do is you can directly find the argument from here, okay? Or what you can do is you can consider what is the, so this was the initial argument and how much it has moved, right? And you can subtract that. That will also give you the argument, right? So this is how your reflection coefficient will look like at 0.1 lambda. So that's how you use Smith chart to evaluate the different parameters. Okay, clear? Is it clear? Yes. Okay. So now this is another question. Okay. So this time, because it would be difficult, within presentations to give you time to solve because these things are graphical things. So what I've done is I have already shared the solution and we'll discuss the solution so that things become clear. Okay. So this is another given, some given circuit. And here we know this is your ZL. Okay. So here you remember this shows that it's already normalized. You don't have to normalize it again. So this is your normalized impedance. Load impedance. This is your characteristic impedance of your transmission line. This is the length which is given. Now, what is Z at L equal to lambda by 4? So what is Z at this point? This is similar to what we just discussed, right? So if you remember, what do we have to do? First, locate this point on the Smith chart. In most of the cases, when you have to use Smith chart, you have to first locate the normalized load impedance. Okay. So if you locate this, you'll get it somewhere here, right? So now, once you have located the load impedance, what you have to do is you have to go to the WTG line and see what this distance corresponds to, right? And then you have to move by a distance of 0.25 lambda. So as you can see here, this is the point, and then you move by 0.25 lambda clockwise. Remember, you're moving towards the generator, so it should be clockwise, right? So now when you come here, you can find the argument from this point, okay? But what you need is the impedance, right? So go straight down to the circle where this circle intersects, and that will give you the value of your reflection coefficient at L equal to lambda by 4. Right? And this is what you get. Here you are already getting the normalized values because initially it was already normalized. Okay. So this is your normalized Z. Okay. Now, what is the SWR on the line? So what you do, you have to consider the point where this circle, your SWR circle, where does it cut this horizontal line? That corresponds to the maximum resistance that your transmission line holds, right? So this point gives you the standing wave ratio, right? Now, how far from the load is the first voltage minimum? Even this kind of things we can try to solve. So what do we do? What do you mean by the first voltage minimum? So here the voltage minimum occurs where when Z is minimum, right? So what you do is, as this corresponds to Z max, so this corresponds to Z mean, right? Now what it is asking you is that how far from the load is this? So basically what it is telling you is, you know the location of your load from here, from the WTG line, right? And then you can correspondingly find the location of your Z mean point, right? And then you need to find the difference between the two. That will tell you how far you have to move from the load so that you reach the minimum resistance point, right? So this is your distance. This corresponds to your distance D. So whatever the WTG is doing is that it is representing D, which is the distance from the load, representing D in terms of lambda, that is the signal. Okay, so now you are here, you have to go here, so you find the difference, and that will give you the distance from the load where you get the first voltage minimum, right? So we remember this case that there'll be standing waves with a Vmax and a Vmin, and that will be repeated after some time. So when will the first minimum come? It will be at this distance from the load, right? Okay. So similarly, if you have to find the Vmax, what you have to do is then you have to take this entire route, okay, to this point. Okay, so that gives you the maximum, the position of voltage maximum. So that's how from this point you can actually find the positions of voltage maximum and minimum graphically. Okay, so this is another question where again these are the parameters that is given. Now the frequency is specified. We'll see why it's required. And then it says that you have this air filled two line wire with some characteristic impedance and is operated at some particular frequency. Load is given. Now first, obviously, find the normalized load. Do that, locate that. Okay, locate that on the Smith chart. Okay, now what is the line impedance? 2.5 centimeter from the load. So initially this was specified in terms of lambda. In this question, it's specified directly in terms of like length units, right? So what you do is you find the wavelength of your signal. You know the frequency, so you can find the wavelength. Okay, and then see how far is it, right? Sorry. So that tells you that this is the distance that you have to cover, right? So 0.25 lambda distance is the distance. So in terms of lambda, 0.25 lambda is the distance from here to here, right? And now the question becomes similar to what we have just discussed. So you know this point, this is your load impedance. You will find the location of the load impedance. Okay, now you have to move by 0.25 lambda clockwise, right? And then you reach this point. Okay, now this point, if you extend to this circle, that will give you the impedance at that location, right? Basically the same thing that we were doing. And if you now here again, when you do SWR, it's basically this point where it cuts the horizontal axis, right? So that's how you get to this values. Okay. This is another problem which says that now your length is specified, you know what the Z in looks like at this end, right? So the line shows this is 3/8 lambda long and its normalized input impedance is given to you. What is the normalized receiving or load end impedance? So it's the other way around now, right? So now what you have to do is we have to move towards the load, right? Initially in other questions we know this, we were moving towards the generator. Now we have to move towards the load. So just as the other case where you were following the WTG line, here you have to follow the WTL line. Okay, so now what you do is you know the impedance at the input end. Okay, so let's first mark it. So it's J 2.5. So this is your input impedance, like at the input end, this is your impedance. Okay, now that corresponds to some distance. So you know that distance, and this is what you are getting. Now you have to use the WTL line because you have to move towards the load, right? So now this is your, so use the scale which is WTL scale. So this corresponds to this location. Now what this says is that you have to move by this distance, right? So in this case, what you have to do is, now initially we were moving clockwise, right? Here we have to move counterclockwise. So remember, with WTG, it's clockwise. Here is anti-clockwise. Why? Because all this comes up from the phase, right? E to the power minus 2 beta L, 2 beta D. It was a minus when you were moving from the load to the generator. If you do the other way around, it would be plus, right? So that means now you have to move counterclockwise. So from this point, move counterclockwise by a distance L equal to 3 lambda by 8, right? And you reach somewhere here. This is your point again on the WTL line, okay? And then what you do is you extend it to the circle, okay? The same circle that just as we were doing previously. So this gives you the load, the impedance at the load end. Okay, so this is the value. Now, if you have to, this is the normalized impedance. Remember, if you are asked for the impedance, you need to multiply it by Z naught. In this case, they have only asked for the normalized impedance. So this is your answer. Okay. Now, what is the distance from the load to the first voltage minimum? So this is your position of the load. Now, what is the distance from the load to the first voltage minimum? What is the location of the first voltage minimum? This is the location, right? Now, when you find the distance from the load, what you have to do? You have to find the difference between these 2 points, right? So if you take the scale of wavelength towards load, okay, you already know this point. You can similarly find on the same scale, find the distance here, and the difference between the two will give you how much you have to move from the load in order to get the first voltage minimum. Okay. Similarly, if it was maximum, you could have done you in that case, you can locate this position on this line. Remember, this is your WTL line. Locate that point. So that is your load. Now, this will be your Vmax point, right? So then this entire length that you cover, okay, this point, it will also have some. So if you take up this line, right, this will also have a value here, right? So that wavelength, and take the difference of the two, that will give you how far you have to go for the first voltage maximum. Okay. Now it said that what length of open circuit line could be used to replace ZL. So you know the value of ZL. Now what should be the length of your open circuit line so that you can replace ZL? Okay. So from the position of ZL, we want to move towards a new load. Okay. And the new load is the open circuit line. So what is the open circuit line? That is the Z equal to infinity point, right? So until we reach the open circuit line, want to know that distance, right? So if you take that difference, what you see is this occurs as 0.25 lambda on the wavelength towards load scale. So now what should be the total distance? The total distance should be, so this point minus this point, right? 0.064. 0.064 is this difference, right? Now you have to move from this point to here, right? So if you do that, this is the distance that you need to cover in order to replace your ZL by an open circuit. So if you move by that distance, effectively it will be an open circuit. Okay. So these are some basic questions of how which shows how the Smith chart can be used. Okay. Now, one important fact about this kind of questions, or in this kind of circuits, is impedance matching. So basically, as I was initially telling you, your ZL might not match with ZG. Okay. And in general, for any circuit, if you have to have maximum power transmission to the load, your ZL, so given some ZG, your ZL should be equal to the complex conjugate of ZG. Okay. But now also remember that suppose if you have some transmission lines involved, then this matching has to be done at two ends. One is the load end, one is the source end. So your ZL should match with Z naught. Your ZG should also match with Z naught or Z in, right? So there should be a matching at the source. There should be matching at the load. Only then it would be a complete, total transfer. Okay, and how this matching is done through different processes. So one way is to use a transformer. So between the two, you can use a transformer between, suppose here, you can use a transformer in order to effectively make the load look like the source impedance, something like that. Okay, but then this generally works at lower frequencies. Okay, another way is to use a lumped circuit element which involves L and C, so that you have some added impedances which together now gives you an impression that at the load end your total impedance has changed and it effectively looks like the source, so that it matches, right? So that kind of lumped element matching can be done. Sorry, but another thing is that the quarter wave transformer. So what basically this is based on this concept. This is something which we are doing in the last class, remember? So we had some ZL, and then we had this multiple circuits, if you remember. The Z in for one was behaving like ZL for the other circuits. So cascaded circuits. So there also what we saw is, suppose if you know suppose ZG is given. Okay, that means for at the source end, if there has to be a matching, then Z in should look like Z naught, ZG, right? And now suppose if you have your transmission line such that it has a length of lambda by 4, you know that Z in is related to Z naught and ZL by this relation. And for matching at the source end, Z in should be equal to Z naught, ZG. So if you put it here, what you see is your ZL should be, so your Z naught should be given as root over ZG into ZL. So that tells you what kind of characteristic impedance your transmission line should have, and under what conditions your matching is possible. Okay, but remember here, because this the main idea here is that the transmission line has a length of lambda by 4, it's wavelength dependent, so it does not work good over signals which vary over some frequencies or some wavelengths, right? So in those cases, this does not it's not that effective. Another important way is by stub matching. So there can be various ways, but what particularly is important is this single stub matching network, where what you do is you basically add something to this end so that it looks like it has matched. So what you do, uh, for this kind of cases, we try to write your load impedance in terms of admittance. Okay, 1 by ZL, that gives you the admittance at the load end. Okay, similarly your Z naught becomes minus of Y naught. So now so minus just shows that it's it's the admittance loop. Okay, so now what it is telling you is, suppose you know ZL, so there should be a matching which, so it tells us that ZL should go towards Z naught, and again ZG, which is at the source end, should also go towards Z naught, right? So for that, what we do is, in terms of a Smith chart, what we do is, ZL, write it in terms of admittance, and check where on the SWR circle, sorry, it should be circle, not circuit. Okay, so basically what is SWR circle? If you know the value of your impedance, then when you are drawing this circle, okay, with the magnitude of your given impedance, that circle is called the SWR circle. Okay, so check where the SWR circle intersects the unit circle. What is the unit circle? Unit circle corresponds to this circle, right? Somewhere in the middle where you get the point as r equal to 1. That is your unit circle. Okay, so check where that matches with the unit circle and note that point. Okay, suppose that point is some value a in the admit. So remember that now in the Smith chart, you are considering it in the admittance, like as an admittance chart. Okay, so then what you can write it is, you can write it as 1 plus j some b. Okay, so that point, remember, why is it 1? Because you are on the unit circle. You have noted the point where SWR circle matches the unit circle. So at that point, it should look like 1 plus jb. Okay, so now the distance moved from YL to A. This distance. What is this distance telling you? This distance is basically telling you what the distance from the load to the stub should be. Okay, so basically why is this true? Because suppose at this point this is your impedance. Okay, so this is YL that is known to us. So basically we want to make this term 0. What we want is this, right? We want it to match. So we want this term to be 0. So this is all, this is something we need to find. Okay. And this is something, this YL prime is something which we have got from here. So what you write is 1 plus JB plus this term. This is something we need to find. What is the admittance of your stub, or in a way, what is the impedance of your stub? Okay, so that should be equal to 1 plus J0 so that it matches, right? Because this is what you get at this end. Now it has to match with that. So what what this tells you is that the admittance of the stub should be equal to minus of JB, so that this thing cancels, right? So so now the distance that you have to move from YL, okay, YL was this point, the first load impedance point, load admittance point, and to this point, that intersection point, the distance that you have moved, that gives you the distance from load to the stub. Another important thing is what is the length of the stub, okay, and that is given, that is basically related to this B. So it's the distance from the short circuit point, right? Because see, this is what you are doing, right? This zero corresponds to the short circuit point. So what we want to do is from the short circuit point in the admittance chart, okay, to A. A is this point, which corresponds to 1 plus JB. B will come from the Smith chart. Okay. So that distance will give you the length of your stub. So that's how one can find the length of the stub that is necessary. And one can also find the distance from the load to the stub in order to do the matching. So basically what happens here is additionally you have a added stub connected in parallel that in a way helps us to make the effective Z in match with the ZG that is there in your circuit. Okay, so that is how the matching is done. So basically that was about today's class. Okay, so thank you. Any particular thing that you need to ask? Okay, okay. So in that case, let's call it a day. Thank you. Yes, thank you.